Hello, everyone. Welcome, and thank you for taking the time to attend this short webinar on Docker. Glad to see that so many people connected. We still can see some people connecting right now, actually. Kind request, before proceeding, could you please raise a hand or just confirm in the chat window that at least some of you can hear me? All right, I can see a lot of hands up. Thank you, thank you. Whoa, overwhelming my screen here. Thank you, so no issues on my side. I hope everyone is okay in the safety of your homes. So let's get started. Gonna lower all your hands right now. All right, so the purpose of this webinar is to give you a very high level overview on what exactly are Docker containers in general, a few of the inner workings that make containers possible, and how did we end up with this so popular technology today called Docker. And if the time allows it, we will demonstrate some of the concepts at the end of this webinar on a real Docker command line. This is by no means a complete course on Docker, complete training on Docker. You will not become an expert just yet, just to set the right expectations from the beginning. But you will understand some very important concepts to get you started and to allow you to become more friendly with this relatively new technology. Now, a few words about myself. First of all, that's my pre-pandemic face right there from when we used to go out. I started my career in networking more than 10 years ago. I went through the usual suspects of Cisco certifications like CCNA, CCNP, had my CCIE for 8 years now. Then I steadily migrated towards the DevOps realm, and I'm currently a trainer for Docker and for Terraform, which is another future webinar. And in general about container technologies. And for the sake of professional consistency, so to say, I have also recently become Docker certified. And a few words about the DevOps Artisan project, since this webinar is part of this project as well. It was created by BitNet Training, and it was designed with a very strong focus on making people aware of these DevOps technologies, while at the same time ensuring that each training manages to deliver just enough hands-on practical experience. That's because our objective is to train you in such a way so that you also gain the required skill set to apply those concepts in the real world, something that you usually don't get from a simple recording or a YouTube video. Speaking of recordings, this session is being recorded and you will receive an email with links to both the recording and the PDF of the presentation that you're hopefully able to see right now on your screen. If you have any questions, please use the Q&A section or the chat window. I will try to answer those as soon as they are posted. But for more complex topics and scenarios, I would strongly encourage you to use the email address here on the screen so that we don't overstep our allocated time frame for this webinar. Other than that, of course, if you need any other kind of information about our trainings, how will they be conducted, what precise topics will be covered, feel free to use the same email address on the screen. My colleagues that manage the DevOps Artisan project, along with our trainers, will be more than happy to help you and point you in the right direction. So before diving straight into Docker, let's just focus a bit on the larger ecosystem that includes Docker, which is DevOps. Now, the main idea behind DevOps as a movement, so to say, is to bring together two traditionally completely separate types of teams: the developers that write the applications and the operations people, or the sysadmins, the people responsible for making sure that those applications written by the developers will run properly from the developer's laptop, from the first test on the developer's laptop to the data center, to the public cloud, and even sometimes in between. And especially with the introduction of ever-growing public cloud offerings nowadays, the need to increase this ability to automate and quickly deploy infrastructure and services has increased tremendously. Nowadays, when you press that buy or deploy button in a public cloud, you expect that thing that you just bought to be ready right away, or in just a matter of minutes. And traditionally, developers needed to focus just on the code, right? Building the application, testing it, not worrying about the infrastructure that the code runs on. while the other team, the operations people, only took care of the physical or the virtual infrastructure with everything in it, like compute, storage, networking. How do you access it remotely? How do you access it in a secure manner, and so on? So if we were to think of a similar term to DevOps, I would say that DevOps is collaboration between developers and operations. And this is a more natural kind of collaboration. It doesn't just imply communication between these teams, because theoretically we had that already, right? But it's about blurring the lines between these two traditional job roles and also reaching out into the other's area of expertise. So developers now need to understand how a cloud infrastructure works so that they can package their applications in a more compatible manner. Also, on the other hand, operations teams need to understand that they are not simply providing the infrastructure, but now they're tasked with actually running real code, real applications that they should be aware of. So what started as a simple idea of collaboration between developers and operations has grown into a huge ecosystem. An interesting interactive overview of this can be found at this link here on the screen. Digital AI, which is previously part of was previously part of ZB Labs. Of course, a periodic table of elements has nothing to do with DevOps. You could call it a marketing stunt, but it does make for a nice presentation and also points out just how huge this ecosystem has become lately. I could bet that none of you knows or has heard of more than half of these tools out there, which is why I would strongly encourage you to have a look and decide for yourselves where a knowledge deep dive makes sense for you in this ocean of DevOps. Play with this link for a bit, figure out which of these makes sense for you, and your future career. Now, to reach it, either use the link on the screen, or just search for periodic table of DevOps, or just wait for the PDF presentation to arrive in your inbox after the webinar. So to help navigate this DevOps ocean, we at BitNet, and especially the people in charge of the DevOps Artisan project, we have defined several learning paths to guide you in this journey. So all our paths here at DevOps Artisan are aligned with specific job responsibilities and profiles that include the most, we'd like to think that are the most relevant tools out there that we have found in each specific field, taking you from an associate level to an expert level, right? From zero to hero. We cover pretty much the entire DevOps loop, starting from writing and managing the application code, moving on to building and release automation with Jenkins. What else do we have here? Configuration management, right? With tools like Ansible, Chef, Puppet, deployment, Docker containers and orchestration with Kubernetes, monitoring with Elastic Stack, which you might know as the ELK stack, made up of Elasticsearch, Logstash, Kibana, Prometheus for time series databases, and of course security in DevOps tools. By the way, this slide is just the current state of affairs. We're constantly adding more technologies to our offerings, so make sure you use that email address, ask for more, and well, ask for more. So enough marketing, right? Let's move on to today's topic on Docker containers. And in the meantime, a warm welcome to those of you who have just joined us in the last few minutes. The very first thing that you hear people talking about when Docker is introduced is probably going to be something like this slide right here, the difference between containers and virtual machines. And while the inner workings and very low details of how containers work are definitely a topic that you can talk about for an entire week-long training, one of the biggest differences between VMs and containers lies in the operating system. With virtual machines, you encapsulate the operating system in each virtual machine, as you most likely know this already. And those operating systems run on what is called virtual hardware, which is just a software abstraction made possible by the hypervisor. And the hypervisor is a component, well, actually just an operating system in itself, in fact, with some drivers, that slices the real hardware resources of your host, of your server, and presents them as virtual resources to the virtual machines. As a result, Those virtual machines think that they are running on physical dedicated hardware, and they behave and are managed like standalone servers. Now, on the other hand, the other half of the slide, containers do not encapsulate the operating system, but they all run on top of and rely upon one single operating system on your host. So they all share one single OS, and they rely on kernel level mechanisms from that operating system to ensure proper isolation, proper security between containers, and a somewhat similar behavior to VMs. This is why you'll encounter terms like OS level virtualization, or user space virtualization, or isolated user space instances when reading about containers, because it's actually a type of virtualization that happens on top of the operating system. Now, the next question would be something along the lines of, okay, so what are containers good for? And since we have a slide like this, where we introduce containers by comparing them to VMs, you might think that, well, containers could be used as a replacement for VMs, right? Well, the answer is yes and no. Yes, you could use them as VMs, and no, you should not. And the reason is that the reason behind this statement is the fact that containers were not designed as a replacement technology for virtual machines. In fact, containers were designed to focus on one single application inside each and every container, one single application at a time. And a very important benefit of a container technology such as Docker is standardization, just like shipping containers, right? Like the ones on this picture right here. Docker containers are just a standard box, quote unquote box, right? That behaves in the same predictable fashion, predictable manner, all the way from the developer's laptop to the customer's private cloud or to the public cloud, which of course means that the container is supposed to be portable, very easy to distribute, right? And by packing just the bare minimum amount of configuration files, dependencies, libraries, whatever you need to run a specific application, they can be lightning fast to spin up, to destroy, to restart, to move from one host to another, to update, all the daily operations, right? All the ops in the DevOps. Those operations that used to take minutes or tens of minutes with booting up or restarting virtual machines or migrating virtual machines can take as little as sometimes even under a second when running in containers. And speaking of the fact that they're easy to distribute, in fact, a lot of open source applications nowadays, and you might have noticed this, especially in the past few years, a lot of the open source applications nowadays are shipped over the internet and distributed over the internet directly as containers. Actually, I've encountered on several occasions, a lot of software pieces, not only libraries, but actually software tools out there that when you go to the installation page and their official documentation, the first thing they show you is how to run it in a container. And then if you really want to, if you don't have a containerized environment, then okay, this is where the source code lives in GitHub. This is how you pull it on your machine. This is how you run it, maybe compile it and so on. But for the most part, a lot of the new tools that emerge nowadays are designed to run in a container from the beginning. And long gone are the days when you run into dependency or library version issues when running multiple apps with different requirements on the same VM. Each container is now a completely separate and minimal environment. No more dependency hell, right? Where specific applications require specific library versions that at some point are going to clash with one another or with other applications and their requirements on the same VM, right? Also, being so fast and lightweight, containers are designed to be ephemeral, disposable. You should design your containers so that you can destroy and rebuild them at any time on the same host or on another host or from your local environment to the public cloud. And being so lightweight makes them play very nice with orchestration tools like Kubernetes. But that's a topic for a different webinar. So what's inside Docker? Well, inside Docker, from a very, very high level perspective, you're going to find two main components. You have the client, which is just a program that you interact with whenever you run your Docker commands. And you have the server or the daemon. That's the component that actually listens for those commands coming from the client or from any other client that is able to send proper REST API requests. Having this REST interface between the client and the server also means that you're not restricted to the Docker client when interacting with Docker. There are many tools out there that can talk to your Docker server and manage your containers. Actually, Docker is entirely made up of a pluggable architecture. So all these components here that you can see on the screen, there are actually many more than you can see on the screen. All these internal components can be easily replaced as needed, right? Not just the client. The server is also the one that manages all the inner workings of Docker and manages objects like images, containers, of course, things like networks, volumes, cluster-related entities, and so on. Consequently, a Docker host is nothing more than a server. It can be physical, it can be virtual, Docker does not complain, that is running a Docker server installation on top of a Linux or Windows kernel. Yes, Docker containers are natively supported on both Linux and Windows. Finally, another component that is not actually part of the Docker installation itself is that registry on the right. That's the place where Docker images live. By default, this is going to be Docker Hub, a public registry, very similar to GitHub, completely free, but for Docker images instead of code. And you can also install a registry on premises if you want. You can have them all in-house, on all the deployment in-house with different features, depending on how much or if you want to pay for it, right? In my opinion, the most important thing to mention when talking about the technology behind Docker is the fact that Docker did not bring any new technology to the table. It simply made it easier for everyone to use some features that were already there in the Linux kernel in order to provide virtual machine-like isolation and security between containers. So in order for this to happen, Docker took some of the technology already available in the Linux kernel and kind of abstracted it, wrapped it nicely, right, in a user-friendly way, so that nowadays when you just want to containerize an app or just start a container, you don't have to worry about all these low-level details. They are still there. It's just that Docker takes care of them for you. So let's have a look over some of these examples here, specifically namespaces, C groups, and some file system features. Let's see what exactly is going on behind the scenes with Docker. So first, we have the concept of namespaces, which in Docker is actually the namespace feature in the Linux kernel. You probably know this. What is the purpose of a namespace? Not just in Linux, but in many programming languages out there. Well, a namespace's purpose is to avoid naming collisions. And let's take the first example of a namespace, like the process namespace, the PID, as an example. You know that every Linux system starts with just one process ID. It could be init, or more recently, it could be systemd, which has process ID 1. That's the root process, and it's used to launch the rest of the system. Now, if you create a container on that parent system, the container still needs to believe that it is an independent system on its own, right? We have isolation in place. But by default, there is no hard isolation like with virtual machines between the processes running inside the containers and those running on the host. In fact, every process that you start inside of a container is a process that gets started on the underlying host, as well as gets the next available process ID, right? Remember, we just have one single operating system. So containers need to believe that they are an independent system. So they need process ID 1. But since we cannot have two processes with process ID 1 on the same host, well, this is where namespaces save the day. Namespaces isolate each container so that there is no conflict between process IDs inside the containers and process IDs that are visible on the host. Now, each container gets its own PID1, can get its own PID1 right now for its main application, while on the host, on the left-hand side of the graphic right here, that very same process gets the next available PID number in the main operating system, just like any other process. And the example depicted here on the slide only refers to the process namespace and isolation, but the same principles, the exact same principles apply to network interfaces, to file systems, mount points, inter-process communication, host names, users, and so on. Basically, we have all the isolation in place that simulates what we previously had with virtual machines and kernel isolation, except that we're doing this on a single operating system without isolating the kernel. So containers running on a host, as well as the host itself, share the same operating system and the same resources, right? Like CPU and memory. But by default, there is no limit to these resources. A container can end up using all the host resources. To control this behavior, we have another built-in feature of the Linux kernel called control groups or C groups. Now, traditionally, C groups are used to provide a sort of a fair share allocation of resources when you're running in a multi-user environment, but this can be easily translated to containers. So Docker uses C groups to restrict the amount of hardware resources allocated to each container, and also lets us define some fair sharing of those resources among containers. Of course, this helps with not only keeping track of resource usage. A lot of people end up deploying containers and then wondering, well, I wonder how can I see how much resources my containers are eating up, right? So what's the general status of my host? How are they doing, right? But also helps avoiding, let's say, runaway containers or so-called noisy neighbors that might end up using too many resources. Maybe perhaps due to a software bug, maybe to an infinite loop or in the app or some container that might have gotten compromised and suddenly started, I don't know, mining Bitcoin or Dogecoin, right? So besides namespaces and C groups, we have one more construct, which is not really a requirement for containers, but Docker uses it for image and container management. That's a layered file system. And before speaking about it, we should briefly mention what exactly is an image from Docker's perspective. Now, a Docker image is just a minimal set of files on your disk. That's it. It includes code, some libraries, some dependencies, everything that you're required to run a very specific application. Remember, containers are focused on one single app. So everything that you package inside of an image and everything that you run inside of a container is destined just to provide the bare minimum necessary resources and libraries and dependencies for that specific app. Of course, this also includes the app itself, right? And this is why Docker is sometimes considered a technology for packaging applications, because everything is neatly packaged inside these images. Now, Docker images have layers, just like onions and ogres. And each layer usually adds more content to the image and builds upon the previous one. And all these layers in an image are read-only. They're read-only in order to preserve the integrity of the base image. So what do you do with these images? Well, you use them as templates to start running containers based on them. There's no limit to the number of containers that you can start from a single base image. So what actually happens every time you run a container based on an image is that the image file system is mounted read-only inside a container, and a new writable layer gets created on top of it for each and every container. This is actually the only layer that can be changed by the container every time files need to be created, changed, or deleted, because everything else is read-only, right? And in order for this to actually work and to become sufficiently transparent to the user and the app, this is where the copy on write mechanism comes into play. If a container needs to change a file from the read-only image layers, for example, the default configuration file, then the container first needs to make a copy of that file to its writable layer and then change it in place. This also means that the writable layer lives only as long as the container exists. But the moment you delete or recreate that container, the contents of that writable layer are lost. So if you have multiple containers started from the same base image, one writable layer per container is created, but that image is only stored once on your disk and also is shared by all the container instances that use it. Finally, where do we get these images from? And the good news is that it's extremely easy to find already Dockerized applications on the largest public and free image registry out there, which is called Docker Hub. Now, in some aspects, it's extremely similar to GitHub, if you ever used it. And it's not the only source out there. There are registries like these from all major cloud providers out there, like Amazon, Google, Oracle, Microsoft, and so on. You can also host your own registry in your own data center. Just to have a look, this is Docker Hub right here, accessible at hub.docker.com. The first page here actually shows my my repositories. But if I go under the Explore section, the first one on the uppermost menu, you see that we have access to over almost 4 million Docker images right here. All right. Now, if you scroll just a bit through these images here, you're probably going to recognize at least a few of them, like PostgreSQL, the Ubuntu Linux distribution, Redis, Node.js, MySQL, and so on, right? Golang, Java, BusyBox, and a lot of the tools that you're probably already used to leverage in software development and software distribution for compiling code and so on. All right, and without going into too much detail right here, if you just look under one single image like Ubuntu, you can see that it's actually a collection of images right here, that it's available for a multitude of architectures, right? 386, ARM, IBM Z, PowerPC, and so on and so forth. So that's another interesting piece of information here. The fact that containers can actually, Docker can actually run on a multitude of architectures are out there, from the Raspberry Pi to the public clouds, right, instances. I'm also going to find some tags in here, which are actually just a way in Docker to differentiate between different versions of the same parent image. So, for example, for Ubuntu, probably know this. We have this versioning scheme here, like 1804, 2004, and so on. These tags right here actually point to a specific image. In order for you to actually get the specific distribution that you want to use. You can also use as a tag the name, the Xenial, Bionic, and so on, the names that are given to these Ubuntu distributions here. We'll go back to Docker Hub in just a moment. So containers, as I mentioned before, are designed to be destroyed and recreated at any time. But we just saw that deleting a container removes all the contents of its writable layer. So all the files that our container has changed or created are lost. So how would you be able to run a container that serves a web page or a database, right? What would be the point if you lost all that important data every time you recreate or update your container? So for things like user data, databases, and many other types of content, we need a persisting object, a persistent type of entity in Docker with a life cycle that is completely independent of that of your containers. And that is a Docker volume, a storage entity that you can mount into your containers and provide them with persistent storage. A volume can be as simple as a path on your Docker host, or can point to a network location. It can even mount memory-backed volumes that are not stored on the disk. Very useful for passing sensitive information inside the containers, like configuration files that include admin passwords, like root certificates, stuff like that. So there's a lot of flexibility here as well. Now, what we've managed to briefly cover so far is nothing more than the tip of the iceberg, right? We're just scratching the surface of what container technologies include, of what you can do with them, and what tools you have at your disposal. There's just so much more when it comes to Docker and containers in general. You have networking for your containers to talk to each other, go online and be reachable from the internet in order to actually serve something if you're running servers in your containers. You have security features like traffic encryption and some features borrowed from the security principles also in the Linux kernel. Things like AppArmor, SE Linux, or the IP tables firewall. You have ways of designing and creating and building your own images using Docker files and to interact with image registries. You have compose files and Docker stack. They're both methods for deploying applications in a declarative manner. And also clustering multiple hosts together for high availability, orchestration. If you want to integrate them with CI/CD pipelines, there's just so much more. And again, we're just scratching the surface here. Now, since I promised a demo, let's focus on some very simple but handy Docker commands. Now, first, the general syntax of Docker commands is quite simple, and it's just a matter of referencing an object like a container, an image, a network, any type of object in Docker, and then action, right? So Docker object action, and an action to perform on it. You can start or stop a container, create a network, connect to a network, download an image, and so on. All right. So for example, let's jump here to a command line. Right, I hope the font is big enough for everybody to be able to read it. Some of the outputs of Docker can be pretty wide. That's why I'm not exactly increasing the font any larger than this because it's going to wrap around the screen. So first of all, I am running Docker on a Mac right here, as you can probably guess from how the title bar looks like. One word of advice, even though Docker for Mac actually runs just like Docker on any other type of operating system. In the backend, if you look under preferences here, in the backend, it actually uses a very small and lightweight virtual machine. That's because macOS, while being a BSD distribution at its core, doesn't exactly play by the same rules that Docker expects to find in a Linux kernel, right? So that's why when you actually install Docker for Mac, it's going to automatically install a small lightweight virtual machine just for the single purpose of providing a valid and a functional Linux kernel that can be used as a base operating system for all your containers. This is also something that you will see on Windows. If you install Docker for Windows, it's going to look pretty much the same. But if you have a look under Hyper-V Manager on Windows and you try to run a Linux container on Windows, you will be able to, but you will see a virtual machine, a small Linux virtual machine being started automatically within Hyper-V. All right. So keep in mind, we do have native Linux containers. We do have native Windows containers. Anything in between, right, has to be done by means of a workaround. So that's Docker for Mac right here. So simple commands, right? For example, just listing objects in Docker, right? If I want to list, for example, my currently running containers, I'm going to do something like Docker container ls. You can see Docker tries to borrow some of the commands from the Linux world so that people are going to adapt more easily to these commands. And I can see that I don't have any containers currently running, but I do have a lot of containers that were running at some point, and I can list those with Docker container ls -a. This also lists the stopped and exited containers. You can see a lot of containers here. Launched a lot of stuff on this machine in the past 4 months or so, but they are all exited. You can see under the status section here, they are all exited. So they have run at some point in time, but they have exited in the meantime, or have been created and never launched. All right. Another useful command would be to list what images I currently have. So what images I can currently leverage in order to start containers based on them. That's a list of images right here. As you probably remember from the examples that we looked over when we visited Docker Hub, first have a repository section on the left, like Ubuntu, right here. And then we have a tag, the second column on the right. And again, we can see that we have an Ubuntu latest, and we have an Ubuntu 16.04. Right now, I believe latest is somewhat similar to 20.04, if I'm not mistaken. But nevertheless, this is where you can see what images you currently have on your machine, what images you can use in order to start some containers. I can very easily download some more images. That's going to be a simple command like docker image pull. So for example, if I want to download something like Ubuntu, let's see, 18.04. Fix the typo in there. I'm going to see that these are actual file system layers. If you manage to catch the output before it concluded here, it said pulling file system layer. Now, this specific image right here has 4 layers, right? These are those read-only layers that we talked about earlier. So right now, I have a newer image downloaded. You can see it only took like, I don't know, 5 seconds or so. No authentication required. Actually, you don't need anything, just a valid Docker installation. You have access to all that tremendous amount of Docker images on Docker Hub. You can also push your own images as well, just like with GitHub. Whatever is public is fair game for everyone, right? If I just look at our images one more time, you should be able to see that right now I also have an Ubuntu 18.04 downloaded right here. You can see that the images for Docker are actually quite small in size, right? 64 megabytes in size, right? Quite small. All right, what else we can do? Now, let's try running a simple container. Again, running a simple container is going to be just a matter of typing Docker, an object that we want to work with, which would be container, right? And an action. What would be the action? Well, run. So Docker container run. And the simplest thing that you can actually run in a new installation just to check that everything is working properly, is going to be a hello world container. And of course, this is not going to be, this is quite underwhelming, right? Nothing spectacular here. It's just a container that prints something on the standard output, right? Gives you an output here. We could have done that with an echo command, right? But it's very good for testing a first time that everything works well from the first time, that the client can talk to the daemon. And also, if you read through this message here, it's going to provide you some very tutorial-like output, right? It actually tells you what happened here. You have a Docker client contacted the Docker daemon. The daemon pulled the hello world image from Docker Hub. Well, in my case here, even though the hello world image is extremely small, I actually had it already, so I did not have to pull it anymore. You can see the architecture. Then the Docker daemon or Docker server created a new container from that image, which runs an app, an executable that produces the output you're currently reading, right? And then, of course, that output for us, in order to be able to see it, was streamed to the Docker client, which you are using, to your terminal, right? So again, nothing terribly spectacular here, just something that we could have done with an echo command. So let's try something more interesting, or just like the output says, to try something more ambitious here, all right? So let's try running something like, let's go back here to Docker Hub for just a second. We should be able to find the Alpine image. You're probably going to find the Alpine image referenced in a lot of tutorials, blogs, and trainings all over the internet, because it's a very, very small image. It's actually based on BusyBox, as far as I know, and it actually has a lot of tools in it. Surprisingly many tools for such a small image. You can see it's only 5 megabytes in size, right? An Alpine image. So let's try running an Alpine container. Actually, it's part of the Alpine Linux distribution, just like Ubuntu, just like CentOS, Oracle Linux, and so on. All right. So by using what we know so far, Docker object action, Docker container run. What exactly do we want to run? Alpine. All right. And apparently nothing happens. So what happens here? The reason that we don't see any kind of output, and apparently nothing actually happened, is that when we're trying to run an Alpine container, the main application for this container, just like with all the other generic Linux distributions out there, like again, Ubuntu, CentOS, Fedora, Red Hat, whatever, the main application is going to be a shell, right? If you run an operating system without any graphical interface, the first thing that you're going to see, the only thing that you're going to see after you start that virtual machine is going to be a shell, just like with containers, right? The first thing that the container attempts to start when I tell it run an Alpine or an Ubuntu container or anything else is going to be a shell, right? Well, what is the purpose of that shell? And when I say shell, I actually refer to something like bash or zsh or ASH or any other type of shell that might be found in a specific Linux distribution. So what's the purpose of a shell? Well, the shell receives commands from the standard input, executes them, and then outputs whatever happens to show up at the standard output. Well, the caveat here is that by default, Docker will not provide the standard input to the application that it's running inside of a container. So the shell will have its input stream closed. So what happens when the standard input is closed on a shell? Well, the shell exits. And since the shell is the main application inside of a container, the container exits as well, right? Remember, the container is just an environment for a specific application. If the application is not there anymore, there's no point in having the container running either. And actually, in order for me to prove that this is the case, I can do a Docker container ls -a and an L at the end just to show the last container that I attempted to run. And you're going to see an Alpine container created about a minute ago. Sounds about right. So this is probably the one that I tried to run about a minute ago, exited about a minute ago. And the actual field that's interesting for me here is the command section. The command here tells me that when this container started, it attempted to launch this /bin/sh executable. It might be a symbolic link. I don't really care. It's something that can be executed when the container starts. And well, remember the discussion that we had like 2 minutes ago about launching a shell with no standard input? Well, the container attempted to launch this shell, found the standard input closed and closed the shell. Well, when it closed the shell, the container exited as well. Because again, the container is just an environment for a specific application. In this case, the shell. If the application dies, there's no point for the container to keep on running. All right. So the right way to actually run a container with a shell is going to be by adding this -it flags in the middle right here. What this does, it's actually, you can use it as a mnemonic, right? And think of it as interactive, launching an interactive container, but it's not actually interactive. The I actually stands for keeping the standard input open, and T actually to allocate a sudo TTY, a virtual terminal, so that you can actually send and receive commands to that standard input, right? If I do this, then I suddenly find myself with a different prompt, and right now I'm inside of the container. Not sure if Alpine has something like, let's see, does it have something like this? So Alpine release is going to tell me that it's actually this is the version of this Alpine container right here, right? This Alpine distribution. Now, this would be a great time to actually demonstrate those namespaces as well. Remember that namespaces, those things in the Linux kernel that provide isolation between resources on your host and resources inside of container. Right now we are inside of container. So I'm just going to open another prompt right here on the right. And the right-hand side is now my MacBook, right? It says here, Andrei MBP. So this is my host, okay? On the left-hand side is my container denoted by this pound hash sign right here. So let's see, for example, file system isolation, right? Let's look at the root of the file system on my Mac. Well, nothing amazing right here. You can see it's actually very similar to any Linux file system. But if I do the same thing inside of a container, there's definitely going to be a difference, right? So you can see that from this simple command right here, that the container actually sees a different root file system than my host. You can see the folders are not the same, the owners, the permissions are not the same, the dates are not the same. It's a completely different root of the file system. Where does this file system come from? Well, from the Alpine image. Something else. What was another namespace? Let's see, for example, the process namespace or the PID namespace, right? Let's list all the processes on my Mac, right? PSAOX on the right-hand side. Whoa, right? That's probably, I can see that I have a bunch of processes in here running in the tens of thousands with their PIDs. That's probably because I restart my machine once a month or something like that. But you can see that there are a bunch of processes running on my host right here. Let's do the same thing inside of the container, PSAOX. Whoa, okay. How many processes do I have inside of this container? Well, you might be tempted to say 2. I would say I only have 1, the shell, as you can see, because the other one, PSAOX, was actually the command that I ran to display this output right here and exited right after it finished displaying it. Right. So again, this is process isolation as well. One more. Let's look at the network interfaces. Gonna type ifconfig on my Mac. I'm going to get a bunch of network interfaces in here, physical, virtual network interfaces, VMware interfaces, tunnels, and so on and so forth. Actually, I have no idea why there are so many, but let's do the same thing, the same ifconfig command on our Alpine container, if I manage to type it correctly. And we're going to see a completely different set of network interfaces. Well, you probably recognize the loopback. That's just a software interface here. And there's an ETH0 interface, which allows my container not only to talk to other containers, but also to go online, right? And also to serve some clients on the internet, or to go online and download some packages, download some code, and so on and so forth. All this networking here, what happens behind this ETH0 interface is managed by Docker, all right? So let me exit here on the right. Gonna exit for this container as well. So we saw how to run an interactive container, right? I can also run Ubuntu containers like this. You can also run pretty much any major Linux distribution out there, because most of them will try to run a type of shell, right? So this is how you can run most major Linux distributions that you can download from Docker Hub. Now, what about something else, right? You might want to run at some point a server container, right? So in order to run a server container, and when I mean server container, I'm referring to something like a web server, a database server, something that, you don't have to launch it and then interact with it. You just want to launch it and then forget about it for the next 5 years, right? Like a web server, right? How to launch a web server? Well, in order to launch a web server and not end up being attached or connected to that web server, just send it to the background, the right term in Docker is to launch a container in detached mode. So for this, again, Docker object action, Docker container run. I'm going to add the -d right here. This one actually means detached. Launch a container in detached mode. And I'm going to launch a very common web server image, which is Nginx. You can probably find it on the first page on Docker Hub. It's very widespread. And I'm also going to do one more thing, right? Everything that happens within Docker pretty much stays in Docker, right? So if I just launch this web server, it's not going to be accessible for anybody except me on my Docker host, right? In order to make it accessible, I can actually forward a port 80, right? That's the Nginx is going to listen on. I can forward it outside and map it on my host so that any other client from the outside is going to be able to access my container. In order to do this, the syntax is quite simple. It's -p, right? Followed by the port that I want to map on my host and the port that I want to forward inside of my container, right? Let's run it like this. Now, it does return me to my prompt, so it doesn't connect me to the container, but it also provides me with a unique ID in here. This is the actual ID of the container. Now, if I have a look at my running containers, I'm going to see that I currently have a container based on the Nginx image, which starts with this ID right here. You can see the first 10 characters or so. Created 16 seconds ago, so this is definitely my container here. Also, because these container IDs here are pretty hard to work with for human beings, Docker is nice enough to provide you with some human-friendly names, sometimes even funny names. This distracted Euler is now our Nginx container. You can also see under the port section that I have mapped the port 80 on my host, accessible on any interface, to port 80 inside of the container, all right? Which means that I should be able now to go back to my browser and try to access localhost. And I can see the default web page that is served by my Nginx container right here. All right. Now, this is pretty much how you will be running most of your daemon containers, most of your server containers. So you can run a MySQL container, a PostgreSQL container, an Apache container, a Redis container, anything that actually is designed to run as a daemon and to accept connections from the outside. That's when you will use this detached mode right here, right? This container here is actually going to run indefinitely unless, I don't know, something crashes in it, if the host crashes or if the admin intervenes, all right? So you can see that it's still up and running and will be up and running as long as it can. Now, one more thing I wanted to show you is a bit of a nicer way of interacting with Docker. Of course, the command line is very powerful, just like in any operating system, with any tool out there. But there are a lot of other tools, even tools that are running within a container that can manage your Docker installation. One of those very nice tools is called Portainer. And I believe I already have a container, so I'm simply going to start it. And let me head back to my browser, and instead of let's actually open a new tab here. I believe that one is on port 9000. Let's check it right here. Yes, we actually have two forwarded ports here, 8000 and 9000 for Portainer. Let's go to 9000. There you have it. Actually, you have a quite nice web interface right here that's managing my local installation of Docker. And you can just click through everything, right, available to Docker. You can see here on the left things like my current containers, right? These are all the containers that I have currently defined on my system, be them, I don't know, created, running, or stopped. You can see that the two running containers are the actual Nginx one that I've just launched a few minutes ago, right, with port 80 being forwarded. And the other one is this container, right? The container that I'm currently interacting with, the Portainer container. You can see that's the name of the image as well. So if you want to launch this one, it's going to be a Docker run, Docker container run, followed by some arguments, and then Portainer/container. Again, another image that can be easily found on Docker Hub, completely free. And other things like images, networks. I haven't talked about networks, but they're a very strong topic with Docker, and it has evolved tremendously over the past period. Volumes, remember volumes, right? We mentioned the volumes when we talked about ensuring data persistency, because containers are supposed to be destroyed at any point in time. So you're going to lose that writable layer, you're going to lose that container, and you have to be okay with it. And in order to be okay with it, you can use volumes. Volumes ensure that your data stays safe even after a container gets destroyed and recreated. One of these volumes you can find right here is this Portainer data volume. This one is created automatically when I install this web application that you're currently seeing. Why is that? Well, you probably noticed that I'm currently logged in with the admin user, and I had to enter a password in there. So that's user profile information. That sort of stuff has to be stored someplace permanently. I don't want to just destroy this Portainer container and lose all my settings, lose all my user accounts, and so on. That's why Portainer actually creates a volume for this, which is mounted from this location right here. Actually, we can dig into it for just a bit. So locally on my machine, the volume is just a location in my file system. Within the container, it's actually mounted at a specific mount point right here on the bottom of the screen. Sorry about that. Let me go back. So it's mounted under data, right? This is where the container can write files, can change files, can make any type of changes, and those changes will persist no matter how many times I destroy that container. If I update Portainer, knows that there's a new version available, and in order to install a new version, I'll just have to download the image again and start a new container based on that same image using the same volume right here. And I will still have access to every other settings, any other settings that I have previously defined, all the users that I've defined, right? Another type of object here, I'm going to find config secrets, swarm. These are all related to clustering, running Docker on multiple hosts at the same time. So we're going into the realm of not just clustering, but even orchestration, work scheduling, self-healing apps, scaling apps, and so on and so forth. But that's a discussion for a dedicated training, and also for Kubernetes. Right now, I am part of a swarm or a cluster, but I'm the only node in that cluster, so it doesn't exactly make sense, but it still shows up here on the left. All right. So Portainer, if you are scared of the Docker command line, give it a chance. On the official documentation for Portainer, one of the first things that you can see whenever you go to the documentation section is a simple command that you can paste into your Docker command line. And that simple command is going to launch this container for you. It's going to automatically manage your entire installation. Very powerful. Now, finally, one more thing that I wanted to show you. And that is compose files. Compose files, like the one I have right here, and actually, let me show you the contents of this. A compose file, it's allows you to describe not just containers, but actually more than containers, like networks, volumes, rules, everything in a single file, an environment, a complex environment in a single file. So instead of typing hundreds of Docker commands by hand, launching containers, creating networks, configuring networks, connecting them to networks, mounting volumes, and so on and so forth, you can actually have all that information inside of a single file right here. All right. Usually, this complex environment might be a single larger application, maybe with many components, just like the example that we see right here on the screen. We actually have a WordPress and the MySQL install, right? So we have under services section, I have a DB service, which is actually nothing else than the MySQL image 5.7, the Docker image for MySQL here, and then WordPress, which is based on the whatever latest image is available for WordPress. Now, even if we're not going to dig into so much detail about this, the syntax of this Docker Compose file, you can see it's YAML, right, from the syntax and from the extension. You can probably figure out what these are, right? So environment variables. This is actually a very nice way that's available to us on a lot of Docker images. You can find this information in the on Docker Hub under the documentation for each image. A lot of Docker images allow you to configure them when you launch the container by setting specific environment variables, right? So that you don't have to go inside the container and change some configuration file. Because if you ever installed WordPress, you probably know that, you unzip that zip file with all the PHP files, and there's a config PHP somewhere in there. You have to open that one and fill in the where is the database, what's the port, what's the username for the database, what's the password, and so on and so forth. Well, this is not the right way to do things with containers. Because again, containers are supposed to be replaced at any time, rebuilt at any time. So you don't go in a container and start changing stuff, because you will lose those changes when the container is rebuilt. So another very elegant way is to provide that information by using environment variables. And a lot of the people, the smart people that have packaged those applications as Docker images, have made sure that there's a startup script in there inside of the image that actually looks for these environment variables and properly configures your app according to whatever is set under these environment variables in here, right? Other than that, you can see that the database container has some volumes. Again, makes sense, a lot of sense to have a volume for a database so you don't lose the database. What else do we have here? Have a dependency. Depends on DB, which actually means I'm going to start this container only after I made sure that the container for the database is up and running, right? There are a lot of things to discuss here, but that's the gist of it. And ports, right? We're forwarding some ports. So for example, WordPress here is going to run on port 8080 on my host, mapped to port 80 inside of the container, so that I can access the WordPress installation on port 8080. I don't have something similar for the MySQL service. That's because I don't want the MySQL service to be accessible from the outside world, right? I just want WordPress to be able to talk to it. And the way this environment here is set up, there's absolutely no problem for WordPress to talk directly, the WordPress container to talk directly to the database container. And also, it can reference it using its name. You can see that the actual content for the WordPress DB host environment variable is not an IP address followed by a port, but it's the name of a container, name of the service right here, followed by a port. And that's a standard MySQL port, by the way. So in order to see how this works, it's actually, I would say, painfully simple, but it wouldn't make so much sense, right? It's going to be a matter of just typing Docker compose up. All right. Is it done? Pretty much. Right. Let's go back to our website here, web browser. Let's have a look under localhost, this time 8080. And there you have it, a working WordPress installation. How long did it take? I don't know, 3 seconds maybe? Right, I had the images already downloaded, right? You could say I cheated for just a bit. But just downloading a couple of tens of megabytes for the MySQL image and for the WordPress image, especially since you only have to do it once, the very first time, it's not exactly going to be something terribly difficult, right? And this is actually functional here. So let's try using something like this. Probably going to forget that password, of course. So let's install it. All right, let's log in. And there you have it. It's actually running, right? That's the actual WordPress site. And the previous one was the admin section. Look how fast that was. And by the way, you can also get to see the tremendous amount of logs generated by MySQL and WordPress as well, right? Let's just shut it down. And that's it. Now our WordPress is not working anymore. Let's see what else do we have running in here. We have Portainer and Nginx. We can simply remove it. So for example, we can use something like Docker Container RM, forcefully remove it if it's currently running. So let's remove the distracted Euler. Let's go back here, refresh, and it's gone. And just for the sake of diversity, let's just stop the Portainer one. Look how fast everything is. Actually did not have to wait more than a couple of seconds for anything, for any type of app, for any type of shell to be launched, for any type of Linux distribution to launch. Even for two containers like a web server and a database, we did not have to wait more than a couple of seconds, right? So let's go back here. Now, as I said before, this webinar was just about scratching the surface of Docker. I tried to cover as many relevant aspects as possible, but there is a huge amount of topics to be covered before you can master Docker. So for an in-depth view and for more practice and less theory, send an email to askformore@devopsartisan.com. Make sure you ask for more, and my colleagues, myself included, will be more than happy to accompany you on this journey. All right. So thank you so much for attending this webinar. Thank you for spending a bit of your time, which is probably the most expensive resource on this planet. And I truly hope I managed to make it interesting, useful, and a time well spent. So if there are no further questions here, enjoy the rest of the day. Go play with Docker on your Windows or Mac laptop. It's very easy to install. It's free. And perhaps we'll see each other again in a dedicated by the book Docker training in the future. Right, so thank you so much, and hope to see you on a future webinar or maybe a future custom training. Thank you. It's a question here in the chat window. Apologies, I think I skipped one or two questions in there. Question says that addresses if we can run Windows images on Docker. Well, yes, you can, but keep in mind that you are actually running a specific piece of software that was designed, was compiled for a specific architecture or operating system. So in order to run something Windows specific, you are going to need a Windows kernel, right? So that's where Docker for Windows actually comes into play. There is native support for containers on Linux and on Windows, right? So you will have to have a proper installation of Docker on Windows in order for you to have the kernel from Windows that allows you to run Windows containers. Docker Hub is the exact same location for both Linux and Windows containers as well. I would warn you that from a Windows perspective, I would say Docker is not as capable or as mature or as fast as it is with Linux, because containers appeared on Linux, were meant for Linux, were born in Linux, but they are possible on Windows as well. Just keep in mind, if you want to run a Windows container, you're going to need a Windows operating system. If you want to run a Linux container, you're going to need a Linux operating system. All right, so hopefully this answered your question. Let's see, we have another question here. How do you run multiple subdomains and web apps on the same server and the same port? Well, if you want to run multiple applications on the same port, normally I would say it's much better to use different ports, right? And maybe have some proxy in front of it, like a reverse proxy that actually delivers specific requests to specific web apps. Now, there are also some very smart ways of doing this with Kubernetes, in which you can actually deploy something very similar to an application load balancer that can look at the URL and figure out which application that URL is supposed to connect to, right? So that would be some way of running multiple applications on the same port, or at least on the same port that is exposed to the outside world.